The first very example which has been given to you about the formation of HCl and formation of NH3. Okay, so in the formation of HCl and NH3, they are saying that these reactions are possible, but we are not able to tell that whether reaction is slow or fast. Okay, so to understand these kind of things, we are going to start the chemical kinetics chapter. Okay, so, what is the reaction mechanism? What is the rate of reaction, and what steps are involved here? These these topics are going to be discussed. Some terms are going to be used like feasible, not feasible, spontaneous, non-spontaneous. So that means feasible and spontaneous have somehow they have same meaning, like the anything which is happening on their own or anything which is possible. So if I am saying that HCl is feasible, that means HCl is able to form. If I am saying HCl is spontaneous, then that means HCl is making out by its own. We are not pushing any temperature and pressure to H2 and Cl2. It is just forming by its own by the time H2 and Cl2 makes contact with each other. Okay. Do
Okay.
you got it that what kind of introduction in chemical kinetics is what we are exactly going to study? Can you tell me? I mean, can you give me the idea of what I have told you just right now?
Um, just like what are chemical kinetics?
Yeah. What is exactly chemical kinetics?
Um, so it's basically like it has to do with like the rate of the chemical reactions. Um, and then like what affects that. So like how quick the reactants are like converted into products, and then like all of the different steps.
Yes. So basically, reaction rates, reaction mechanism, rate laws, and simple models are going to be discussed here. Okay. So the very first part is reaction rate. I'm saying it again. I'm saying it again and again. Reaction rate is the important part. These have the several classifications. Okay. So now, what is the rate of reaction? Any time by which reaction forms, whether it is decomposition or whether it is combination. For example, if any product is forming, so at what rate it is forming, it is a rate of reaction. Any any compound is decomposing, so at what rate it is decomposing, that is the rate of reaction. Okay. So, as an example, it has been given to you nitrogen dioxide is decomposing into nitrogen oxide and oxygen molecule. That means it is a decomposition reaction and it has some particular reaction rate. Okay.
Okay.
So now we have a formula by which we calculate the reaction rate. So we are not able to find the if we are not able to find the concentration of any reactant, for example, let's say that is a NO and O2. Okay. So NO has been formed, NO has concentration, NO has some concentration at some time. O2 has some concentration at some time. So we will just uh, find out the difference between these two concentrations. Okay. So am I audible now?
Yeah.
Okay, great. Because to me it's kind of a glitch. Okay. Okay, wait a minute. I got a glitch. My whole screen is stuck. Okay. Until now, I'm just narrating my statement. Okay. So reaction rate has been said as the formula, and the formula is change in concentration with respect to time to the ratio of the time taken. For example, uh, we have a concentration of NO at time 1. We have a concentration of O2 at time 2. So concentration of time 1 subtracted by concentration of time 2 divided by the whole time. Once we get the numerical, we will able to solve it. Okay. So the difference between the concentration and dividing it by time, we will get the rate of reaction. Got it?
Okay.
That's a very simple one. Okay. So the reaction rate of any chemical reaction can be defined as the change in concentration of reactant or product per unit time. Any concentration of reactant is decomposing and any concentration of product is forming to the ratio of time is the rate of reaction. It is very obvious that in a reaction, reactant will always decompose and product will always form. That is the ideal condition to make a reaction possible, right? Reactant should decompose and product should form. So reactant decomposing per unit time, product forming per unit time is the rate of reaction. Okay.
Okay.
Now, the concentration unit should be in mole per liter. Okay. That we have to remember. So now you can see the reaction is still same. The decomposition of NO2 is giving NO and O2. Now we have been given with the concentration of all these, uh, what we say, like reactant and product also. We have a time. So at 0 second, NO2 concentration was 0.01, 0.0100. Okay. But the NO and O2 concentration is zero because at time zero, reaction has not started, product has not formed. So the reactant is still intact. As soon as we increase the time, we got to know that reactant concentration is decreasing and a concentration of product is forming. So now you can see by the increasing of time, the concentration of reactant is decreasing and the concentration of product is increasing. You can see at any random time. For example, let's say at 150 second, the concentration is now very much decreased as comparison to the 0.01. It is now 0.005. And the concentration of NO has been increased and the concentration of O2 has also increased. Okay.
Okay.
So now we got to know that reactant concentration will always decrease in the form of graph because in the order to form the product, reactant should decompose. So now in the graph, you can see the reactant is decreasing. This is the graph of NO2. Okay, the green line is showing the NO2. Okay. Now, so basically in the graph, if any line is starting from above to the down, that means it is decomposition and it is very obvious it is reactant. Okay. Now let's discuss about the uh, red and blue line. So these are the product because products always starts from scrap. At initial time, they was at zero concentration. Okay. As soon as we increase in the time, the concentration of product is getting increased slowly. So now these are the concentration of NO and O2. Okay. Concentration has been given to you. You can see NO concentration is always greater than the O2 concentration. You getting it?
Yeah. Okay.
NO concentration is always greater than O2. It is just a data given to me and we are just making the graph of this. So NO concentration is always greater than O2. That's why NO graph is somehow uh, in a greater extent than O2's graph. Okay, you got it?
Yeah. Okay.
Any doubt?
No.
Okay, so can you explain it to me that what we did here? Start with the formula of rate of reaction.
Um. So the formula is just like the um like change in the concentration of one of the like reactants, and then you would divide it by like the different times. So the change in time.
Yeah, right. And what about this graph?